Okay, so I'm going to quickly go over the ransomware scripts so you know how it works and that you can see that it works as well. So first of all, the attacker would have a script like this to make two asymmetric keys using RSA. So we've got a script here called RSA _private _public keys. What this script does is it creates two RSA keys, two asymmetric keys. So we've got a private key here and we've got a public key. This is what the attacker would do on their machine before anything else. So once the attacker has done this, they'd have their ransomware, and we've got a ransomware here. This script is what will be on the target machine and what is going to encrypt all the files, encrypt the system, and also decrypt the system. And the way it does that is we use the cryptography.fernet. So we're using the Fernet encryption module, and it encrypts all the files with one key, and it decrypts all the files with the same key, and that is what we're going to call the Fernet key from now on. So this ransomware script generates a Fernet key, and then it generates a Fernet encryption decryption object, which is the cryptor. So this script will encrypt all the files with the Fernet key, and then this ransomware will be packaged with the public key that we created, our RSA public key. So once it's encrypted all the files with the Fernet key, using the Fernet key, Fernet object, we encrypt that key with the public key. Now the public key can go out to many machines. It does not make a difference. As long as we keep this private key private, and on our machine keep it to ourselves, that's fine. So now when the target machine is encrypted and the Fernet key that was used to encrypt those files is also encrypted with the public key, then they will obviously get a ransom note, and they will send off that Fernet key, which is encrypted now in a text document. They'll send that off to our encrypted email like Proton Mail or something, and then the attacker will use this script. So we've got the attacker script create two keys, we've got the target victim script which will run the ransomware using the Fernet key to encrypt and decrypt files, and then we have another attacker script. So when they send that encrypted Fernet key to you, you will then use the private key which you created in here. First of all, you'll use the private key to decrypt that Fernet encrypted key, and then you'll put it into a document called, for this tutorial, it's put_me_on desktop, and then you'll send that through email back to the target. And then obviously the way the ransomware script works that I created it, they put this text document with the unencrypted Fernet key on their desktop, and then the ransomware software script will eventually unencrypt all their files and unencrypt their system. But obviously that would only work in real life once they pay the Bitcoin. So that's a quick overview of the 3 files that we have in this tutorial, in this ransomware tutorial. So I am actually going to go and run this code now and show you that it does work. And also, just a quick note, I haven't actually seen a tutorial on ransomware like this on YouTube, so I think this is a first, and I hope you enjoy. So let's begin with showing you that it works. Now we're going to actually run the ransomware and see how it works and that it does work. So now I'm going to play as the attacker at first. So what the attacker would do is they would run the RSA private public key script to create two asymmetric RSA keys. So we'll do that first. So I've got script here, and we'll run the script. Shouldn't take too long, and as we can see, we've got our private key and our public key now. The reason for this is so that we can encrypt the symmetric Fernet key in the ransomware that is used to encrypt and decrypt the files and the system. Once the Fernet key has encrypted the files and the system, we will use the public key to encrypt that key. So as an attacker, I would now package the ransomware with the public key and send it off to whichever target machine or victim that I was trying to get some ransom off. So we'll just pretend that I've packaged it up, blah blah blah, and now I'm going to act as the victim that has actually got the ransomware on their machine. As a victim, we're going to be using the local root directory which I set up for this example, because obviously I don't want to go through the whole of my D drive or C drive. Inside this root directory we've got files and folders. Inside the text documents we have got lorem ipsum. Now this text is inside all of the text files. They're all the same, just have different file names. As you can see, we've also got a PNG file which is of a hacker manga girl of some sorts. We've got folder 1, exactly the same deal as before. Just have a look at the text quick. Yep, lorem ipsum. And we've got folder 2, which is the same as before, just different file names. So the ransomware will be encrypting the text documents and it will be leaving the PNG files. So that's so we can make sure that it works and it only encrypts the file extensions that we tell it to. As we can see in the ransomware, if we have a look, we've got file extensions here and we've got txt. So it's only going to look for file extensions with .text and encrypt them files. Right. So we're playing the victim now. We've got the ransomware on our computer. So I'm going to run the ransomware now. So the ransomware is running. And as we can see, background has changed to ransom. If I just quickly minimize these, backgrounds changed to ransom. Web browser popped up with Bitcoin, so that they know what Bitcoin even is, because they may not know, and that's not really going to help us. And also the ransom note also pops up, and if we exit, say, the ransom note, it will pop up in 10-second intervals as well. Now it usually does pop up on top of the window, but it can be a little bit buggy, and it didn't do it this time for some reason. But anyway, so on the ransom note, we've got some stuff about military grade encryption. It doesn't really matter if it's true or false, they really won't know, will they? And also we've got some instructions, 3 easy steps. 1, it says email the file called email_me.txt at the desktop /email_me.txt at get your files back Proton Mail. So let's have a look at the desktop and see what's there. For this example, I'll just quickly explain this. Actually, we've got the ransom note, we've got a Fernet key. That's the key that was used to encrypt all the files. It created Fernet _key where the ransomware script would be saved in the system, but that is encrypted now as well. That's just a backup key in case they're stupid enough to delete the key on the desktop. Now on their desktop, I've got a folder here named desktop, which I'm using as the desktop, but obviously it would be their desktop. And we've got email here, email_me. This actually was from before, so I'll just delete that. We've got email_me, and this is the key that was used to encrypt their files, and it's been encrypted with that public key that we created first of all. So if we go to step 2, it says you will receive your personal BTC address for payment. Now with Bitcoin, when you have a wallet, you can have many address wallets, wallet addresses, etc. Obviously you could do some sort of make some sort of software to link up each target machine with the specific encrypted key to a specific Bitcoin address, so you'd be able to match whether they have actually paid, whether a specific target machine has paid to a specific Bitcoin address. You'd know if they've paid. So let's just say I'm a victim and I've paid. It says I need to email the file, one email_me.txt, which is at desktop email_me.txt. So I would email this to the attacker. Step 2, I paid a Bitcoin, and then I email them back saying paid. Now the attacker will check. So, and then step 3, you will receive a text file with your key that will unlock all your files. So now I have sent that email me off to the attacker. I'm now going to switch to the attacker from the victim. So now I am the attacker. I've just received this email that says email me. This is the key. We're going to unencrypt it and give it back to them because they have paid their money. So now we will run one sec. Yeah, decrypt _ Fernet key. So we press enter. Okay, I just realized, yep, I'm the attack. When I was the attacker, I got this email _me, and I'm going to pull it in the folder that I'm doing this example in so that I can actually unencrypt it. Just realized. So yeah, they just emailed the attacker email _me. He takes that file and then he unencrypts it. I'm putting it into this ransomware software folder, which is where my decrypt file is at, to decrypt email _me. So we'll just run that again. We're going to decrypt the file, and as you can see, we just decrypted email _me, and we created a file called put me on desktop. And it also, we just printed out the key just to show. So in this file that we just created is the unencrypted Fernet key, which will be used on the target machine to decrypt all the files on the system. So now, as the attacker, I just created this, I will send this to them in an email. So now I'm going to switch back to the victim, and I've just received an email which has put me on desktop. So I'm going to do what they say. I'm going to pull it on desktop. I'm going to my desktop and I'm going to pull it onto the desktop. But before I do that, actually, let's just check, make sure all the files are still encrypted. We've got bank is encrypted. Hair, yeah, it's encrypted. The PNG file, not encrypted. So the ransomware has worked, as we can see. Encrypted. So we'll put this onto the desktop now and see if it decrypts the files. And it's going to check every 10 seconds whether this file is on the desktop, and when it finds it, it will then decrypt the files and the system. So we will go back to the local root, and then we'll check the files. As we can see, we've got lorem ipsum now. So obviously the ransomware has decrypted the files, and yeah, this is how basically a ransomware works. I'm sure there's other ways you can do the decryption and the sending off of the key, etc., but this is the way that I come up with, and it's fairly easy to do as well. So yeah, and there we go. That's basically the ransomware working. So now we're going to move into the code and have a look at that. If you're enjoying the channel, if you're enjoying the tutorial, please leave a like, leave a comment. Let me know if there's any other sort of subject you'd like me to do a tutorial on, and I will. Everyone should leave a like on the favourite subject on the comment section. If you'd like to donate, I have Bitcoin and PayPal here on my channel. Bitcoin address is there, and PayPal if you'd like to help out and support the channel. Okay, so first of all, we're going to start with the RSA asymmetric encryption, basically. So we've got these libraries up here. We're using PyCrypto. I think the library is PyCrypto for Python 3.7, but still you import the same as you do with the older versions. So we've got from crypto.public key import RSA, that's the encryption. We've got from crypto.cipher import AES PKCS something or other. That's for padding. AES we're not actually using in this, but basically just import all this and we're good to go. So to generate the key, all we have to do is do key equals rsa.generate and then 2048, and then what we're going to do is we're going to create a private key and a public key. as you can see here, this is creating the private key. Private underscore key equals key dot export underscore key, and we're writing it into a .pem. PEM is privacy enhanced mail. That's what it stands for. Basically, we write the private key to private.pem, and then we create our public key and we write that to public.pem. So I'm going to go and run this code, and then we will continue with the rest of it, because we use this at the start of the attack, so to speak. So running the code, shouldn't take too long, and it's finished already. So as we can see here, we've got private.pem and public.pem. Now I'm going to open these up just to show you what's inside. So private, as you can see, we've got the private RSA key and the public key, which is the key that we give out. It doesn't matter if people get hold of it, as long as we keep the private key safe. This is the public key that will be used to encrypt the Fernet key in the ransomware. So I've got a test Fernet underscore key.txt here with an actual Fernet key, and we're going to encrypt that now with the rest of the RSA code. So I'm going to comment out this. We don't need to generate a key anymore. We don't need to create a private key or a public key. I'm going to uncomment out this. Okay, so now we're going to encrypt the Fernet underscore key, like we do in the malware in the ransomware. So we get our public key and we import it. So we've got rsa.import underscore key open. And then we have our public.pem, and we read the data. That's our public key. Here we're going to open up the Fernet key and read binary, and we're going to read the data. So Fernet underscore key is the data in there. Then we need to create our public encryptor like object. So we use pkcs.new public key, and then we're going to encrypt the key, and we're going to save it as enc underscore Fernet underscore key.txt. We're going to write the binary, and we're going to do public underscore encryptor, and then we're just going to do dot encrypt, and then the Fernet underscore key, which is the data and is this key here. So we'll go ahead and we'll run this. And as we can see, it's encrypted. We've got public RSA key and then we've got the memory location. We've got the Fernet key here in bytes, binary, whatever, and it's base64 URL safe encoded, blah blah. And then we've got the key encryption completed. So here we have the Fernet key. We've just encrypted it into this encrypted file. Open it up anyway, and as you can see, the key is very different to what it was because it's all encrypted. This is exactly what happens inside the ransomware code itself. Okay, so now we've encrypted it. We're going to do exactly the same, except we're going to decrypt it, which is not much different, except for we are changing the file name. We're opening up the encrypted underscore Fernet key text document. We're getting the encrypted data. We're getting our private key, and we're importing and opening up the private.pem, reading that data. We create a new crypto object with our private key, and then we're going to just do .decrypt, and then the encrypted Fernet key, which is the encrypted data. And we're also going to save it to a new file, which is dec underscore Fernet, basically. So I'll just save that and run it again, and as we can see, decrypted private RSA key is at this memory address, private decryptor, decrypted Fernet key, we printed out the key as well, it's here, decryption completed, and as we can see, we got dec underscore Fernet. We look at the decrypted key and it's back there, and it's exactly the same as the original Fernet key, and the encrypted Fernet key is gibberish. So at the start of when I was showing you how the ransomware worked, we created 2 keys using this. Then, once the ransomware has done its job and encrypted all the files, we then encrypt the Fernet key that was used to encrypt the files with the public RSA, which is basically this, to encrypt that key, that file. Then once they send the Bitcoin and they send the encrypted file with the encrypted Fernet key, the attacker would use this to decrypt that Fernet key. So we'd get back this and we'd send this back to them. They stick it on their desktop and decrypt their system. So now we're going to move on to the actual Fernet encryption, which is used to encrypt the files and the system. So we'll move on to that. Now we're going to have a look at the actual Fernet symmetric encryption, which is used to encrypt the files on the system and decrypt them later on. So it's simple as well. We are going to use this module cryptography.fernet, import Fernet. And then we've got key. So to generate a key, we just do fernet.generate_key. Then to create the cryptor object, which will encrypt and decrypt using the same key, we just create a variable. I call it cryptor, and then we just do fernet, and then we give it the argument of key, which is the generated key. So we're going to save that to a text document called fernet_key, and we're going to write the binary. Then we're going to open up a picture, which is this picture here. We're working inside this folder here as well, so we've got the script, we've got a picture we're going to test it on. This picture is of the ransom, which was used for the background, and we're going to read that data. So we're going to read all this data that shows the picture, and then we're going to create a new file called enc_pic, which is encrypted pic. We're going to write the binary, and then we're going to encrypt the data from the picture that we just read. We're going to do by doing cryptor.encrypt and then the data. Then we're going to do f.write and then the encrypted data to enc_pic. So let's do that now. As we can see, it says the key. We printed out the key and it says encrypted. We've created a fernet_key.text with the Fernet key that was used to encrypt the pitch.jpg. We'll have a look at the encrypted pic, and it's not going to load, obviously, because all the data has been encrypted, so it doesn't know what to do with it. And it says error code will load in the image. That's fine. So now we can comment out all this. And even though the file ran and completed, because we have the key saved to a file, we can now read that key from the file, use that key, create another Fernet encryptor decryption object by doing key equals f.read from the fernet_key.text. We create a Fernet encryption decryption object, Fernet, and then argument key, cryptor. Then what we're going to do is we're going to open up the encrypted pic. We're going to read the binary, data equals f.read. We're then going to create a new file called dec_pic, which will be the decrypted picture. We're going to write the binary. Then we're going to say decrypted data equals cryptor.decrypt, and then the data, which the data will be the encrypted data. So we're going to decrypt that encrypted data, and then we're going to write that decrypted data to dec_pic. So we'll save that and we'll run it again. And as we can see, dec_pic is the decrypted picture, and we've got the picture back. So we had the original picture, which was this. We then encrypted it using our Fernet_key, and then we ran a new script because we had the key saved, and we used that key to create a new Fernet object to decrypt the picture, basically. So that is simply put, how we encrypt and decrypt each and every file in the ransomware script. We just literally go to root. When we go to encrypt the system or decrypt the system, we start at root and we recursively go through each folder, each file, looking for the specific file extensions which is in the ransomware script, and we encrypt them, or depending on if we're decrypting them, we'll decrypt them. And that's the simple of what we do basically. Okay, so now we're on to the actual ransomware script itself. Now there is a lot of code here, and I'm not going to sit and type it all out whilst you follow along. I don't really see the point in that, as there is a lot of code and I don't fancy just typing it out again. But I will go through it and explain it, and hopefully that will help you out a lot more than just watching me type. These are the libraries that we are using. I'll go through them now. We've got cryptography Fernet. That's obviously to generate the Fernet key, generate the Fernet encryption decryption object, which is used to encrypt / decrypt all the files. So we just decrypt files on target system. We got import OS. That is to basically get the sys root, which would be the system root. So that's why we use that, to get system root, which is obviously be used if you want to encrypt the whole system, starting from the root and recursively go backwards. Web browser, that's another good module. We use that to load up the user's browser basically and go to a specific web page, which in our case is the Bitcoin web page. So to load web browser to go to specific website, e.g. Bitcoin. Now import C types. What do we use that for? Okay, C types, that's basically so we can mess around with Windows DLLs. That's so that we can change the background on the Windows machine, etc. So we can interact with Windows DLLs and change Windows background, etc. Okay, urllib.request. What's that for? Okay, we use that in this script so that we can go to a specific website. We grab a specific picture of our choice. Obviously I chose the ransom picture. We use urllib.request to download and save that image, and then we use that image with the C types to obviously change Windows background. So used for downloading and saving background image. Requests, what's that used for? Right, so requests, that's used so we can maybe get the IP address of the target machine, and then we can see if it's part of say like a government or military or hospital IP space. You know, you might want to if it's in a certain IP space, say military or government, you might want to pass on encrypting it, or you may go for just them, you know, I don't know. But that's what that is for, and we use that with actually self.public IP, which I haven't actually used in this script, but you know, possibly you can do what I just said if you wanted. So used to make get request to api.ipfi.org to get target machine IP address. Time, that's an easy one. That's just used to so we can do like time.sleep, so we can set the intervals for the pop-up of the ransom note, and also the interval to check the desktop for that specific file, which decrypts the system once they obviously pay and send off their encrypted key by email. So used to time.sleep interval for ransom note, and check desktop to decrypt system /files. Date time. Date time I actually don't think I used. I was going to use it. I was going to give like a time limit in the ransom note of like maybe like a few hours or days. I actually didn't bother doing that. Must have forgot. It's not a big deal, but that's what it would be used for. To give time limit on ransom note. Subprocess, that is to open up Notepad and the ransom note file. So to create a process, to create process for Notepad and open ransom note. Cool. Win32 GUI, that is used so we can get the foreground windows. Basically we check what windows are open, and if the notepad, if the ransom note is not on the top window, we will then kill the sub-process of the notepad and then create another process for that notepad so that it comes on top of the window. If Win32 GUI does find that the notepad is on top, it will just leave it. So used to get a window text to see if ransom note is on top of all other windows. Now this is just the public and private key encryption and decryption. So we know what that is. Threading, that's used at the end so that we can keep the ransom note every 10 seconds popping up, and check the desktop every 10 seconds for the decryption key. So used for ransom note and decryption key on desktop. And base64 I think maybe used somewhere in there for some reason or another. So that's why we've got the libraries and that's why we're using them. I'm now going to go through the ransomware itself, which is made from a class called ransomware. So let's get on to that. So basically how I come around to making the ransomware is I broke it up into sort of like little sections, little bits. So here we've got file _ extensions, which is pretty obvious. Basically we put the file extensions of what we would like to encrypt in this list. You can also inverse it and do the opposite, I suppose. They could be files that you don't want to encrypt, and you can encrypt all the other files, so it's really up to you. For the example I just did extensions that I want to encrypt. So we'll move on to the next bit. A lot of this has got comments as well, explaining quite well what the code is doing. If you do get stuck or you need a reference to what it does, it's all got comments through the code anyway. But yeah, when we initialize the instance of the class, we create a key encryptor object, which will be the Fernet encryptor decryptor object, and obviously the public key, which is our RSA public key. They're all set to none at first when we instantiate that class, that object. And we've got a little warning here, which is about the root directories. Obviously you want to use self.local root, and I'll show you where that is used as we go through the code. If you accidentally use sysroot, you'll be pretty screwed. But you'd have to change that physically yourself in the code anyway, so you should be okay. And then we've got obviously self.public IP. That just makes a GET request to this website here, api.epify.org. If you don't know about that website, it just comes up with a plain HTML page, and the only text it has in that page is the IP address that GET request was made from. So it's good for getting public IP addresses on target machines, etc. And like the comment says, you can check that IP to see if it's in the IP space of, say, government, military, etc. in case you wanted to maybe skip sending your ransomware to them, or maybe you want to search for them, I don't know. Next, we've got another method, and it's an instance method because of the self, and it generates a symmetric key on the victim machine, which is used to encrypt the victim's data, and later on it will also be used to decrypt the data. So we've got self.key, and we generate our Fernet key, and then we got our self.cryptor, and we just create a Fernet object with encrypt and decrypt methods. So they were none, and now we've given them value. Next, we are going to write the key. So we're going to make sure we save that key to a text file, just in case anything happens. Plus, we will need it later on anyway. So we do fernet_key.text, and we write that to the text file. These are not in the exact order that the ransomware works, because obviously when we generate the key, first of all we are going to encrypt the files and the system, and then we write the key, and then straight away after we write the key we encrypt that key. We don't leave the key on the system whilst we're encrypting. We also don't change the background on the system or put the pop-up come up before we've encrypted the files or encrypted the key. Yeah. Anyway, move on to do the next method. This is the method that encrypts the Fernet key here, which encrypts that Fernet key. So we open up the key, we read the binary, Fernet key, we just read that file and it reads the key. And then we write back to the same file name, and this is where we use our public key. So we've got rsa.import_key. We open up our public.pem, we read it, create a public cryptor, RSA cryptor, using this line here. We then encrypt the Fernet key by doing public cryptor.encrypt, and then we just give it the value, give it the argument of the Fernet key, which was read earlier. And then we just write that encrypted file, that encrypted key data back to the file with the same name on it, basically. And we also create another file, but this time it's on the desktop, and it's called email_me.txt. And it's exactly the same as we did with the original Fernet_key.txt. We encrypt the data and write it back to the Fernet key, and then we also write that encrypted Fernet key to email_me.txt on the user's desktop. And as you can see, we are using self.sysroot, and obviously self.sysroot up here is os.path.expand_user, and this little funny character, I can't remember what it's called, but it finds the root, the system root directory of the machine you're on, and that is how we find the desktop. And obviously this email_me.txt file is the file that they will have to send you for them to get a decrypted key in a file back from you to put on their desktop. Okay, and then also we do self.key equals, and then we make the self.key equal to the encrypted key. Just for good measure, we also remove the cryptor and make it equal to none once all the files have been encrypted, because there's no need to keep that, just for good measure, why not? So next we got the Crypt File. This is no different to the first example that I showed you with the Fernet encrypt decrypt on the picture when we encrypted and decrypted that picture. It's no different to that. We are doing exactly the same as we did then, basically in here, except it's a little bit less code because I put two into one, you know. Crypt file and then the file path, which will be the whole path and the name, absolute path. And then we've got here encrypted equals false. So encrypted equals false, it's automatically, Crypt File will automatically do the encryption of the file. And then when we want to decrypt the file, we will just do encrypted equals true, and then it will not encrypt it, it will go straight to the decrypt and it will decrypt the file. So that is what crypt_file does, basically. And here we've got crypt_system. That's the same thing, it can encrypt or decrypt depending on encrypted equals false or true. It's automatically set to false, so when we do crypt_system, it will encrypt the system, and then when we do encrypt system and then encrypted equals true, it will decrypt the system. So it just saves you writing two methods, although you can do that if you want. And how we do that is we use the OS import that we imported here to get system root. And we use os.walk, and then we start off at self.local root. So this local root here will start off in that folder that I used in the example, but if you were to change this to self.sysroot, it would start at the machine user root directory, and we got top down equal true as well. So basically what this does is it's recursive, and it basically, we've got for root, directory and files. The files are what we're interested in. The directory will be just the folders, and then root is I can't remember the top of my head, but I'm guessing it's root. Anyway, yeah, it's the start of the path. But anyway, we do for file and then in all the files, because files gives you a list. And so then we get each file in that list of files. We get the absolute path, file_path. We get the absolute path by doing os.path.join. We join root, which gives us the here, which gives us the path of the directory, and then we join that to the actual file name by using file. And then we're just doing if not file.split -1. What that is doing is saying if not, and then .-1 will be the extensions. So like .text, .jpg. By doing split and then the .-1, we're grabbing the JPEG or the text or whatever the extension is, and we're saying basically that if that extension, so if not that extension like text in, and then self.file_extension. So if text is not in, and then that list of file extensions, don't encrypt it, continue. If it is, encrypt it, basically. So that's how we encrypt the system. And as you can see, if not encrypted, self.crypt_file and then the file path, else encrypted equals true. So that's just how we encrypt, decrypt, etc. So next we've got a static method. What a static method is, basically it's just a normal function, but it's part of the class. It's something, it's useful in the class. We put it in the class, made it a static method. This is just using the web browser.open URL, and then the URL is bitcoin.org. That's to show people that may not know what even Bitcoin is, what you're even asking for, some sort of information about it. Otherwise, you know, nothing will happen, obviously, I doubt. And then here we are using the import C types to change the desktop background to like a ransom background or whatever they do. So we're just pulling URL. This is where that image come from. This is the URL. And then we need the absolute path of that image. So we just do sys.root and then I'm just using desktop and then slash and then background.jpg. That's what I'm naming the file, background.jpg. And then we use the urllib.request library by doing urllib.request.url retrieve, and then we've got the URL, image URL, and then the path to where we want to save it, the full absolute path with the file name. And then this is just SPI_set desktop desk wallpaper. That's just a setting. I can't remember what SPI stands for now, but I did earlier. And then we're just using C types, and then we're using C types to access Windows DLLs. And then we're just doing user.32.system parameters info W. I think W is for a 64-bit Windows. If you've got a 32-bit Windows, you've got to change the W to a capital A. And then 0 path 0. The set desk wallpaper will be 20 for everyone, and then 0 will be for everyone. The path, that's going to be obviously where you want to where the file is for it to change the background. It's got to be an absolute path as well, remember, hence why we got that. And then 0. So this will change the desktop background. Ransom note was pretty easy in itself as well. All we're doing is creating a text document like you normally would. We actually don't need that in there because I don't use it. I don't use date either, but I was going to, because you could also give them a time limit. You could say the date today is today, by, I don't know, this day the files will be deleted, there's no chance of getting them back, blah blah blah. So yeah, here we've got the ransom note written out, and we tell them to get the file called email_me.txt, and then we say where the file is at in case they are really blind and don't notice it on their desktop. So we give them the full absolute path. So sys.root desktop./email_me.txt, and then a email to send it to, etc., and some more instructions and whatnot. And then the final, is it the final? Second final, what's it called? Method is the show the ransom note. Now these two are at the end because they both use threading to keep them going every 10 seconds. So to show the ransom note, we open up a subprocess by doing subprocess.popen, and obviously we did import the module subprocess at the top, and then we give it a list here, and the application is notepad.exe, and the file is ransom_note.txt. We've also got a count, which will be used because it only goes up to 5 seconds in this example, 5 times, so it will only pop up 5 times per 10 seconds, for 10 seconds each, between each. And we've got top_window equals win32gui.get get window text win32gui.get foreground window. What that is doing is it's getting the top window that's on the screen, and it's reading the title, basically this bit here. So this is the top window, and it will read that there, and we're comparing if the top window that has the title is the same as ransom_note-notepad, because if you open up the ransom note, the title at the top on the window will be this, for my note anyway, you know, because mine's called ransom_note_note, and it'll be like that. And if it's not equal to that, if it is equal to that, we pass, and as you can see, we print, we do nothing, just for debugging and testing, so we just pass. And if it's not equal to that, we kill the process, and then we start a new process, so that that window will pop up on the top of the screen, so they can't miss the note. And then we sleep for 10 seconds, we add a count to the count up here, and it goes round 5 times, and then once it hits 5 it breaks. That's the show ransom note. And the last but not least is put me on desktop. And basically what this does is it is searching for that file on desktop. When it finds that file, it will read the key, the unencrypted Fernet key. It will then assign self.key back to the contents it's read in the file. Then self.cryptor will create a Fernet encryption decryption object. Then we'll do self.crypt system, and we'll say encrypted is equal to true, so that it decrypts the system, decrypts all the files, and it will just break. And then that is the end of the ransomware, basically. And then we've got a function here which is defmain, and then we've got rw equals ransomware. What we're doing is we're instantiating an object of the class, and then obviously we are using the methods in the order that they go in. So obviously we generate the key, we encrypt the system, we then write that key, we then encrypt that key, change the background, show them what Bitcoin is in the browser, give them the ransom note, then we create 2 threads, we show the ransom note, we write the ransom note, then we show it, and then we check for the file on the desktop so that it can decrypt the system once they follow the instructions. And that is basically the ransomware. So I hope that gives you some sort of understanding of how a ransomware may be made, especially in Python, how it actually works, and how it does encrypt the system and encrypt the keys so that no one else can really decrypt it and they have to pay the ransom, blah blah blah, and all that. It's quite a long video, I know, and it's quite difficult to sort of plan how I was going to make the video because the code's quite long, and it's probably something like this I would usually just upload to GitHub and forget about it. But yeah, I thought I'd show you and make one for you. So yeah, hope you've enjoyed the tutorial. If there's anything else you would like me to make a video on, maybe something that won't take this many lines of code, so I could be a bit more in depth, let me know in the comments, leave a like, sub, all that good stuff, and I'll see you in the next video.